Dr. S. Nagan. He is an associate professor in civil engineering at Tyagarajar College of Engineering, Madurai. He pursued his undergraduate and postgraduate studies from Tyagarajar College of Engineering and completed his PhD at the Madurai Kamarajar University. He has more than 20 years of teaching and research experience. He has worked in many prestigious institutions including PSNA, College of Engineering and Technology, Dindigul. He has published more than 25 research papers and 5 books under his name. Apart from all this, he is a life member at the International Society for Environmental Protection and also at the Indian Society for Technical Education. To add to all of this, he is won the Best Staff Advisor at the ISTE Students Chapter.
Welcome to UGC lecture series for Bachelor of Architecture. This lecture forms under Unit 3, that is of Mechanics of Structures, Deflection of Beams. In the earlier chapters, we have already covered what is shear force, what is bending moment, what are bending stresses, what are shear stresses. Deflection is a criteria which is caused due to bending of beams. When a beam bends, then we call the beam as a deflected, that is, a beam will be subjected to deflection. So, in this unit we will be covering how to calculate the deflection of cantilever beams, how to calculate deflection in case of simply supported beams, and this deflection is essential while designing the beams. In the design of beams, finally we will be checking for allowable deflection. A beam will be permitted to have some permissible limit of deflection. So, after the design of a beam, it is mandatory to check whether the beam deflection is within the permissible limit. If the deflection exceeds, then the depth of the beam or the cross section of the beam need to be modified. So, with that objective, we need to learn how to calculate deflection of beams. And beams, as we know, there will be different types of loading. So, we need to analyze deflection of beams due to point load, deflection of beams due to uniformly distributed load and uniformly varying load, and the same effect of the various loads on different types of beams. So, we will be covering deflection of cantilever beams, simply supported beams, and the methods which we will be dealing with are double integration method, moment area method and Macaulay's method. In the double integration method, we will be integrating twice the bending equation and then we will be arriving the deflection at required values or points. Also, we obtain the slope at required points. In the moment area method, we will be drawing the bending moment diagram with the help of the bending moment diagram of a beam. We will be calculating the area of the bending moment diagram and we will also calculate the moment produced by the area, and we will use that moment of area of BMD for calculating slope as well as deflection. And Macaulay's method is a refined method of double integration which will be used exclusively or which will be most advantageous in the case of simply supported beams, wherein you involve several loads and several portions have to be analyzed for deflection. So, as we discuss, say a beam, if you take a beam, either a cantilever beam. So, either a cantilever beam if you take and let it be subjected to load like this. We have already studied about supports. So, this is a fixed support. At fixed support there will not be any slope or deflection and the beam will get deflected like this. We call this as the deflection curve, and this is one point, boundary point, this is another boundary point. So, at the boundary point normally we will be interested in finding the deflection as well the slope. So, what is slope here? So, this distance is the deflection, and if we draw a tangent to the deflection curve. If we draw a tangent to the deflection curve and measure the angle, that represents the slope and this represents the deflection. So, in this unit or in this chapter, we will clearly calculate or we will clearly see how to calculate the slope and deflection at different points using various methods. So, let us take a first example as a cantilever beam with point load at the free end. A cantilever beam, we are going to analyze a cantilever beam with point load at the free end. The span is L. So, all these double integration method, they involve the general beam bending equation or the differential equation for all fluxural problems we have is E I d squared y by dx squared equal to minus mxx. This is the second order differential equation for beam bending, and when we are able to solve this differential equation, finally we will be getting the value of y, that is deflection, as well we will also get dy by dx, which is nothing but slope. So, all we need to do is we need to substitute this expression or equation and get the required unknown deflection and slope. Again, for deflection analysis, the concept of bending moment becomes essential. Without the value of bending moment, we can't proceed in calculating the slope and deflection, as this equation clearly indicates that E I d squared y by dx squared equal to minus mxx. Mxx is nothing but bending moment at any section xx. So, let us take this example of cantilever beam. Let us consider a section xx at a distance x from the free end, So, we all know that bending moment at xx equal to, normally we proceed from the right end for a cantilever beam. So, similarly, if we proceed from the right end, the bending moment at xx will be equal to load W multiplied by x, and we need to necessarily use some standard sign convention. For bending moment, we already have the sign convention left clockwise, left anti-clockwise, right clockwise and right anti-clockwise, plus, minus, minus and plus. So, if we take bending moment at xx, to the right we have a load of W and the distance is x. So, it produces clockwise moment, and since it is to the right of the section, right clockwise is negative, therefore, mxx equal to minus Wx. When we substitute the value of mxx in the general bending equation, we have E I d squared y by dx squared equal to minus of minus Wx, which will be equal to Wx. This shall be treated as equation 1. In the double integration method, we will be integrating equation 1 twice to get the unknown slope as well the deflection. So, when we integrate equation 1 with respect to x, we get E I dy by dx equal to W x squared by 2 plus C1, where C1 is a constant of integration. Then we need to integrate again the equation 2 with respect to x. Since we integrate twice, the method is called method of double integration. So, integrating equation 2 with respect to x, we get E I y equal to W x cube by 6 plus C1 x plus C2. So, we involve two constants of integration C1 and C2. So, how do we obtain the constants of integration? So, the constants of integration shall be obtained using the well known boundary conditions of the problem. So, if we take cantilever beam subjected to point load, as we discussed initially, it will deflect like this. The beam will be having 0 deflection at the fixed end and it will be having maximum deflection at the load point at the free end, as shown in the figure, and we are measuring distance from the right end, So, we can generate the boundary conditions as, say, at A slope is 0 as well deflection is 0, at B we will be having values of slope as well deflection as seen in the diagram. So, the boundary conditions can be generated as when x tends to L or when x equal to L, your slope is 0. Similarly, when x equal to L, deflection is also 0. So, that can be written as when x equal to L, dy by dx equal to 0, and when x equal to L, y equal to 0. This indicates that there is no slope and deflection at support A, which is fixed. Now, these two boundary conditions have to be substituted in the appropriate equations which we have developed above to get the values of constants of integration. So, let us substitute boundary condition 1 in equation 2. The boundary condition 1 pertains to slope, that is at x equal to L, dy by dx equal to 0, and equation 2 is the slope equation, E I dy by dx we involve there. So, substituting that when x equal to L, dy by dx equal to 0, you will get the first constant of integration as minus W L squared by 2. Now, we can use the second boundary condition, which is the deflection boundary condition, that shall be employed in equation 3, because equation 3 is the deflection equation. So, you will be able to get the value of the second constant of integration C 2 as W L cube by 3. So, once we know the constants of integration, these constants of integration shall be again substituted in equations of slope and deflection to get general equation for slope and deflection. Hence, we get the general equation for slope as E I dy by dx equal to W x squared by 2 minus W L squared by 2. That shall be considered as equation A, and the general equation of deflection will be obtained as E I y equal to W x cube by 6 minus W L squared by 2 x plus W L cube by 3. This is equation B, and the reason why we call as general equation is we can obtain the slope value as well the deflection value at any point of the beam in between A and B using these general equations. For example, if I am interested in slope at the free end, I need to put x equal to 0 in the equation A, that is in the slope equation. If I want deflection at the free end, I will have to substitute x equal to 0 in the deflection equation, that is the equation B. Similarly, if I am interested in slope and deflection at any intermediate point, say for example, I want slope and deflection at the midpoint of the beam, I need to substitute x equal to L by 2 in the slope and deflection equations to get the slope and deflection values at the midpoint of the beam respectively. Now, let us find the slope and deflection at the free end. So, to get slope at the free end B, we need to put x equal to 0 in the slope equation. So, by substituting we get E I dy by dx equal to minus W L squared by 2. Therefore, dy by dx equal to minus W L squared by 2 E I. dy by dx can also be represented as theta, which is nothing but slope, and B indicates that theta at B, that is slope at B equal to minus W L squared by 2 E I. So, this will give you the slope at the free end. Next, to find the deflection at the free end, we need to put x equal to 0 in equation B. Equation B is nothing but the general equation for deflection. Therefore, by substituting x equal to 0 in equation B, we get E I y equal to W L cube by 3. Therefore, y equal to W L cube by 3 E I, and y b equal to W L cube by 3 E I, where y b indicates deflection at point B. Similar to theta b, we have deflection y b. So, now we have arrived in case of a cantilever beam subjected to point load at the free end, which deflects in this manner, the slope at free end theta b equal to minus W L squared by 2 E I, and deflection y b equal to W L cube by 3 E I, where E I represents the flexural rigidity of the beam. A similar term we have AE. AE is also a flexural rigidity, but that is applicable in case of axially loaded members. In case of flexural members, E I is the flexural rigidity. The next case is a cantilever beam with uniformly distributed load. So, let us take a cantilever beam with uniformly distributed load over the entire length, say W kilonewton per meter. Again fixed end is A, free end is B. So, the beam bending equation is E I d squared by dx squared equal to minus m x x. So, we need to obtain bending moment at x x. So, let us consider a section x x at x distance from the free end. So, if you take bending moment at x x, to the right side of section we have load of W into x, that is W kilonewton per meter, which acts over a length of x. So, W into x, and the load acts at a distance of x by 2 from the section. Therefore, the bending moment will be W x into x by 2, and minus sign is due to the moment produced by the load being clockwise, right clockwise. As per our sign convention, right clockwise is negative, right clockwise is negative. Therefore, minus W x into x by 2 or minus W x squared by 2. Therefore, we get E I d squared by dx squared equal to plus W x squared by 2, which is considered as equation 1. We need to integrate twice this equation to get the general equation for slope and general equation for deflection. So, integrating 1 with respect to x, we get E I dy by dx equal to W x cube by 6 plus C 1, that forms equation 2, and integrating 2 again with respect to x, we get E I y equal to W x power 4 by 24 plus C 1 x plus C 2. So, here also we involve two constants of integration, and boundary conditions need to be substituted to get the values of constants of integration. So, the boundary conditions will be, so it is a cantilever beam. So, irrespective of the load, so whatever may be the load, if it is a UDL or if it is a point load, irrespective of the load, the beam will deflect in this fashion. So, always the deflection at the free end will be maximum, and fixed end there will not be any deflection or slope. So, the boundary condition will be again when x equal to 0, sorry, when x equal to L, when x equal to L, the slope is 0. Similarly, at when x equal to L, deflection is also 0. So, substituting the boundary conditions, we will be able to get the constants of integration. So, substituting boundary condition 1 in equation 2, we get C 1 equal to minus W L cube by 6. Using the boundary condition 2 in equation 3, we get C 2 equal to W L power 4 by 8. Substituting the values of C 1 and C 2 in equations 2 and 3, we will be getting the general equation for slope and deflection. So, the general equation for slope is E I dy by dx equal to W x cube by 6 minus W L cube by 6, which is an equation A, it is a general equation for slope. The general equation for deflection shall be obtained as E I y equal to W x power 4 by 24 minus W L cube by 6 x plus W L power 4 by 8. This is the equation B, or the general equation for deflection. Now, once we have the general equations for slope and deflection, and then we can find slope and deflection at any intermediate point or at any required point. So, to get slope at B, that is slope at the free end, put x equal to 0 in the slope equation, thereby we get E I dy by dx equal to minus W L cube by 6, or dy by dx equal to minus W L cube by 6 E I. Hence, theta B, or slope at B equal to minus W L cube by 6 E I. To get deflection at B, put x equal to 0 in the deflection equation, thereby we get E I y equal to W L power 4 by 8, or y equal to W L power 4 by 8 E I. We can represent this as y suffix B, that is deflection at B, which is equal to W L power 4 by 8 E I. So, now when we have a cantilever beam, subjected to uniformly distributed load over the entire span, the deflection will be like this. So, slope at B will be equal to minus W L cube by 6 E I, and deflection at B, this is A and this is B, deflection at B equal to W L power 4 by 8 E I. So, these are the standard loading case for which we have obtained the slope and deflection by the use of double integration method. So, the method double integration means from the name itself it says that we need to do 2 times the integration, therein we involve 2 constants of integration which are solved using the boundary conditions of the problem. In case of cantilever beam, we will have slope and deflection at the fixed end at 0. Using that boundary condition, the constants of integration can be found and substituted to get the general equation for slope and deflection, which we get the values for these 2 standard cases like this. Now, we will move on to a numerical example. Say you have been given a cantilever beam which is 120 mm wide and 150 mm deep and which is 1.8 meter long. We have to obtain the slope and deflection at the free end of the beam when it carries a point load of 20 kilonewton at its free end. So, a cantilever beam 120 mm wide and 150 mm deep. So, it is 120 mm wide and 150 mm deep. It is a cantilever beam. It is a cantilever beam subjected to a point load of 20 kilonewton at the free end. Then the span is 1.8 meter. So, we very well know the deflection pattern. So far we have discussed. So, the deflection pattern will be like this. So, this is A and B. Slope at B will be equal to minus W L squared by 2 E I, which we have derived based on double integration technique or method. So, here W is the load, point load, which is equal to 20 kilonewton and we are expressing as Newton. So, 20 into 10 power 3 Newton. L span is 1.8 meter, which is equal to 1800 mm, and Young's modulus E equal to 200 GPa. So, GPa stands gigapascal or into 10 power 9 Pa, okay, 200 into 10 power 9 and Newton Pascal represents Newton per meter squared. So, when converted into Newton per mm squared, you will get 2 into 10 power 5 Newton per millimeter squared. So, W is given, span is given, Young's modulus is given, I the moment of inertia. So, the moment of inertia I can be computed for rectangular section like using the formula B d cube by 12, where B equal to 120 mm and D equal to 150 mm. Therefore, we can obtain the I value using B d cube by 12, which is 33.75 into 10 power 6 millimeter power 4. Therefore, theta B equal to minus W L squared by 2 E I. Substituting the values, will be getting a numerical value. That numerical value of slope will be in radians. So, we get slope at B equal to minus 0.0048 radians. Next, deflection at free end. So, the deflection at free end Y B equal to W L cube by 3 E I. You know the value of W, we know the value of L, Young's modulus is known and I is computed using B d cube by 12. So, substituting these values, we get Y B, that is deflection at B equal to 5.76 millimeter. So, the numerical values are, say this will deflect like this. So, this deflection at the free end is 5.76 mm and the slope at the free end is 0.0048 radians. So, radians can be converted into degrees and then made use of. So, this is how we calculate the slope and deflection. So, to summarize, we have started with what is deflection and how do we calculate deflection and what is the equations involved. We have E I d squared y by dx squared equal to minus mxx. Mxx is nothing but bending moment at any section xx. So, one should be able to find the bending moment in any section due to any applied loads. So, once we are clear with the finding bending moment and moment of inertia, then we can easily calculate the slope and deflection at any required point. For obtaining the constants of integration, we need to be thorough or conversant with the boundary conditions of the problem. So, we should know how a beam will deflect, how a cantilever beam will deflect and how other beams will deflect. Based on that, the boundary conditions will be generated and used for getting the constants of integration. Once the constants of integration are obtained, substitute in the general equation and generate the general equation for slope and deflection. For numerical examples of standard case, we can very well use the formula derived. For other cases, we need to use either the double integration method by considering sections, or we need to go for moment area method, or we need to use the Macaulay's method in case of several loads. So, we will see another example of a cantilever beam which is 3 meter long, which carries a point load of 20 kilonewton at a distance of 2 meters from the fixed end. Determine the slope and deflection at the free end of the cantilever. Take E I equal to 8 into 10 power 12 Newton mm squared. So, E I is given in this problem. So, a cantilever beam subjected to point load of 20 kilonewton at a distance of 2 meters. Actually, the span is 3 meters. It is subjected to a point load of 20 kilonewton at 2 meters from the fixed end. The fixed end is A and free end is B. So, we need to calculate the slope and deflection at B, the free end. So, let us first compute the slope. So, before computing the slope at the free end, the slope at C need to be computed. Slope at C need to be computed, because say it will be deflecting like this, and beyond the portion C the curve goes simply like this. Since there is no load beyond C, it goes like this. Therefore, the slope, whatever the slope at C, will be the same at slope at B. The slope will not be varying. So, theta C will be equal to theta B. So, we need to obtain the slope at C first. So, slope at C equal to, when you want to obtain slope at C, it is nothing but, say, you can say you have C here. If C is here, then we can very well use the standard formula of cantilever subjected to point load at the free end. So, the formula is W L squared by 2 E I, and here L should be taken as 2 meter and not 3 meters, because the load is applied at 2 meters and there is no load beyond C. So, L should be taken as 2 meters or 2000 mm, W is 20 kilonewton, and E I value is given as 8 into 10 power 12 Newton mm squared. Substituting these values, we will be getting the slope at C. So, slope at C equal to minus W L squared by 2 E I, where L equal to 2 meters, that is the length A C. So, we will be getting theta C as minus 0.005 radians, and theta C value will be equal to theta B, since there is no load beyond 20 kilonewton load. So, if I want deflection at the free end, say load is applied at C, but we are interested in deflection at the free end, Y B is required. Y B is required. So, before calculating Y B, first we need to calculate Y C. So, Y C is deflection at C, that is under the load point. So, Y C can be calculated using the formula W L cube by 3 E I, which we have derived for a cantilever beam with point load. So, W L squared by L cube by 3 E I, where L is this L, or you can say L 1. So, W L 1 cube by 3 E I, where L 1 equal to 2 meters. So, therein we get deflection at C as 6.67 mm. So, we are having this deflection value. So, we want deflection at B. So, that can be found using, say, you have the cantilever beam which deflects like this. We have deflection at C, then I want deflection at B, free end. So, we can easily find this difference. We can easily find this difference by using the theta and length concept. Say we have A, B, C, and we have slope at C. So, slope at C multiplied by the length B C will give the difference of deflection as shown in the diagram. Say here, once we know the deflection value Y C, and we know this value as theta C into B C, that will give you the total, deflection at the free end. So, Y B equal to Y C plus theta C multiplied by B C. So, theta C multiplied by B C is nothing but this is theta C and this is length B C. So, slope multiplied by this will give you the chord length. So, r theta concept, r and theta concept, we have the slope multiplied by the horizontal distance will give you the vertical intercept. So, theta c into b c, we have value y c, we have already obtained theta c. So, and then multiply by the length b c, b c is nothing but 1 meter. So, which is equal to 1000 mm. Therefore, we get deflection at the free end as 11.67 mm. So, to conclude, we have so far studied deflection of cantilever beams by double integration method. We have derived the slope and deflection in case of standard loading, as well we have applied the derived formula to numerical examples to get the slope and deflection. Similarly, we have also studied how to get deflection at extended points when the load is applied somewhere else, using the concept theta and the length. Theta multiplied length will give you the deflection at the other end. So, that concept we have studied, and now we will move to questions. So, the questions will be express slope and deflection at free end of a cantilever beam subjected to UDL. So, these are remember type questions. We need to remember the slope and deflection for standard loading case, and then write the boundary conditions in case of a cantilever beam. So, these boundary conditions which we used while deriving the slope and deflection. Similarly, another numerical example is a cantilever beam 2.5 meters long is loaded with a uniformly distributed load of 10 kilonewton per meter over a length of 1.5 meter from the fixed end. So, a cantilever beam subjected to a load of UDL over a length of 1.5 meters, it is not fully loaded. So, it is loaded over a portion of 1.5 meters from the fixed end. We need to obtain the slope and deflection at the free end. So, using the worked example which we have solved, we can arrive the deflection at B using y b equal to y c plus theta c into the length b c. Using the standard expressions you can arrive. The flexural rigidity, which is nothing but E I, is 1.9 into 10 power 12 Newton mm square. So, when we are able to solve these problems, it indicates that we are confident with the slope and deflection of cantilever beams by double integration method. Thank you.